In problem 12.34, we're talking about everybody's favorite non-planet Pluto, and we have two satellites that are orbiting it. Okay, one of them is a distance of 48,000 kilometers away. One of them is 64,000 kilometers away. Now, Pluto already has a satellite. That satellite is Charon. Charon already has a known quantity. We already know how the distance it is away, 19,600 kilometers. We know its orbital period is 6.39 days. Now, the problem asks us to find out the orbital periods of the two small satellites without using the mass of Pluto. Well, it turns out there's a pretty easy rule to do it. I mean, it took Kepler years of painstaking work, but we can take credit for his work or use his work and figure out what that is. Kepler's third law. Remember, the first ones have to do with the elliptical orbit, and that the sun is at the foci, and that we use gravitational force. But the third one is that the square of the orbital period is proportional to the cube of the radius. Well, that's a good deal. Because if they're proportional, what it means is if I took any two of these things, like if I took any two of them, t1 squared over t2 squared, that's going to be equal to r1 cubed over r2 cubed. Because they're going to make the same proportion. Think of them like similar triangles. You know, that the proportions of the sides are going to be equal. Okay? And that's going to work out awesome for us. So we're going to use the one we know. Charon is T1 every time. And we're going to be able to solve for the one we don't know. So we're going to take, like I said, one is going to be Charon. And let's just do the first one we don't know, 48,000 kilometers. So we're going to say 6.39 days squared over the one we don't know equals 19,600 squared over 48,000 squared. So I cross multiply. I take this. I equals that. Okay. So I'm going to take so 6.3. Oh, these are cubed, by the way. So 6.39 squared times 48,000 cubed is going to equal T2 squared times 19,600 cubed. So all you have to do is take a calculator right now. Take 6.39 squared times 48,000 cubed. Divide that by 19,000 cubed. I'm going to take the square root of that to the 0.5 power, and I get T2 is going to be 25.65, and the units are just going to be this one here, days. So I was able to do that without knowing the mass of anything, which is pretty cool. We're going to use that same trick we used for the closer satellite or unknown satellite with the farther unknown satellite. So we're going to say, again, Charon, we're going to use 19,000. Oh, or not. Remember, the equation is T1 squared over T2 squared equals R1 cubed over R2 cubed. So it's going to be 6.39 days squared over T2 squared equals 19,600 cubed over 64,000 Notice I should put kilometers here. I should put kilometers here too. So just like last time, to get T2, I'm taking the square root of 6.39 squared times, this time is 64,000 cubed, divided by 19,600 cubed. Stay with the calculator, do the exact same thing. 6.39 squared times 64,000 to the third power. I get a huge number in my calculator divided by 19,600 cubed. I get a more manageable number in my calculator. I take that to the 0.5 power, and I got a time of 37.7 days. And again, if you had a telescope, that's a number you could actually check. Not them recommending you do so, just that that's a thing that that even Kepler could check. So that's the way to solve for it, even when you don't know the mass of the planet, as long as you have one known, as long as you have one known period and one known distance orbital.